Hi, today I'm gonna give a short introduction to algebraic geometry codes. So we'll phrase this in classical algebraic geometry, and I'll give a short reminder of some stuff. But probably I'll also cover a bit of this, or cover at least notions of this at some part, or some notions of this in some part of the lecture series, but then the notions will be in the language of schemes. But now we'll phrase it without using schemes. So let's take a smooth curve over FQ, so over some finite field. Let me give you some examples. For instance, we can take the curve by the equation xy is equal to 1, and to show that this is a zero of some polynomial, so we get that this is the zero locus of this polynomial. And now let's check for smoothness. So how do we check smoothness? Well, we just take, we want to know that we have tangents at each point. So we look at the partial derivative with respect to x, and we get, so we look at this, and we get that this is y. Then we do just for y, we get x, and now we wanna, so we get a singular point if it's on the curve and both partial derivatives vanish. So then it would be not smooth. But so for this to vanish, we need y to be 0. For this to vanish, we need x to be 0. And if x and y is 0, we're not on the point, because -1 is not equal to 0. So that's a smooth curve. So let me draw it. That's a hyperbola. So, well, it's hard. That's no drawing in over a finite field, but over R. And let me give another example. Let's take a parabola. So let's take y is equal to x squared. So let's make, and so we get as polynomial y minus x squared. Now let's take partial derivatives. So here we get, with respect to x, would be minus 2x. With respect to y, it would be 1, and here we already see it's not possible that this is 0, so this curve is also smooth. And a drawing, well, you all notice, well, that should be above 0, but you know how it should look like. So that's x, that's y, and also similarly here. Okay, so these are some examples of some smooth curves, but you could imagine other curves. And now let's take a divisor on the curve. So let D be a divisor on the curve C. So a divisor, you can just think of a formal sum of points on the curve with integer coefficients. So NP are in the integers and all but finitely many are 0. And if you know about NP are 0, if you know about finitely about the free abelian group, then you see that this is the free abelian group generated by the points on the curve. And so that's that. Then we can also define the degree of a divisor, so that would be just the sum over the np, so that's an integer, so we get a map degree from the class of, well, not the class, from the set of divisors, so this is a group, so we get a homomorphism to the integers. Okay, so that's the first few things I wanted to say. Now let's go on to regular functions. So we define O of v, let's say, in a little bit more generality. So let's take, we have some variety, and then we take the polynomial ring modulo the idea of this variety. So I of v would just be the functions. So, well, let me maybe write it out. So I of v is the polynomials in here, such that f of p is 0 for all p in this variety. Or you could also think about regular functions. You can show that that's the same. So if you define regular functions, one would define would have to define what a regular function is, but then that would be isomorphic. Okay, at least for algebraically closed field. But yeah. Okay, so of course our finite field are not algebraically closed, but so one has to be a little bit more careful. But let's stick with this definition here. Now the next thing we want to do is we want to look at local rings. So we want to look at points. So localize, let's say, at a point P. What I mean by this is localize it. This maximal ideal. So this is the set of F. So F in, let me write it, F in O of V, such that F of P is 0. So we have a fixed point. And so we localize at this prime, and we get a local ring, which we call OP, which is just O of V, P, so, oh, well, not O of V, P, but O of V, localized at the maximal idea. Okay, so that's, so if you don't know what localization is, you should look this up. So there's a lot of stuff going on actually here. Now this is a discrete valuation ring, so that's also important. So I hope you know what a discrete valuation ring is. So and well, for a smooth curve, and it has fraction field. Oh, I didn't mention it here. I should have mentioned this. So we do not just define O of V, but also the function field, which is the field of fractions of, not of V, of O of V. So that's called the function field. Okay, for smooth curve, and then with fraction field K of V. Okay, and then we can define for f in k of v, we get the order at some point, namely this is just the valuation of f in this ring. It's a DVR, so we get the order. And then we can, now let's go back to divisors, so we get f as the sum of the orders times p. So this is a divisor on C, and so we have seen divisors here, and so of course one would have to prove that only at finitely many points this order is non-zero, and another fact one would have to prove is that the degree of this principal, so-called principal divisor, is 0. So principal divisors are just of the form f for some f in here. So that's the principal divisors. And now we define some spaces, namely the space of elements in the function field, such that the principal divisor is bigger than minus d, or in other words, f plus d is at least 0. So this is pointwise. So we have here some formal sum, and we say that such a sum is at least 0 if, oh well, let's say not such a sum, but rather such a sum, and such a sum is at least 0 if all np's are at least 0. Okay, so we have this space defined, and now that's been a lot of algebraic geometry, but now let's finally get to the codes. So let's take points p1 up to pn on the curve. And maybe you've seen something like Reed-Solomon codes or Reed-Muller codes, and they are some kind of evaluation codes, and we will also define algebraic geometry codes as some evaluation codes, so as evaluation of certain polynomials. But there are also different ways to define algebraic geometry codes. Okay, and we had our divisor D. So the divisor D will now be split into two divisors. Namely, we split into a part where we have a sum over the points, over these points, and some coefficients, of course. And the support, that's another new thing. I'll tell you in a minute what this is. So the intersection with p1 to pn should be the empty set. So the support of a divisor is just a set of points for which np is non-zero, and that's always a finite set. Okay, and now we split this such that this part has support in the complement of this set. Okay, and what we can do now is we can evaluate f, but not exactly. So we could evaluate if we suppose that this, so we could evaluate f exactly if we suppose that this thing here is 0. But we'll define it in a little more generality. Namely, we define it as, oh, I forgot to mention something. So let Ti be generators of the maximal ideal in OPI. So we've seen that OPI is a DVR, a discrete valuation ring. So the maximal ideal is principal, which means that we can take generators of this maximal ideal. Okay, so now we can start to define our code by defining the evaluation map. So this goes from L of D to FQ to the N. So how do we do this? We evaluate f in this L of D by evaluating it at points, and we don't evaluate f, but so these T1 to the B1, so where we have these BIs here, and so of P1 up to Tn to the Bn f at Pn. And why do we define it like this? So we wouldn't need these Ti's if this d double prime was 0, but we want to define it in more generality. So we need these BIs, and to show you why we need it, so f plus d is at least 0, and f plus d is also f plus d prime plus the sum bi pi. And so what we want is that this thing here has a valuation at least 0, and this also, because this means we can evaluate the points. So let's make it, for instance, for the point P1. So we want that the order of at P1 of T1 B1 F should be at least 0, so that we can evaluate this expression, and also for the other ones. Okay, but that's actually in this equation here, because d prime is has support disjoint of this pi's. So we get that from this equation, so this is at least 0, we get that odd p1 of f plus b1 is bigger than 0, but this is exactly the order of f plus the order of t1 to the b1, as this is a local parameter, which means that it generates the maximal ideal, and then the order is so satisfies this relation. So the order of the product is the sum of the orders, and so we get exactly this. So that means that we are able to evaluate these expressions, and we get things in FQ to the N. Okay, that's it for that video. And the next we'll probably see some bounds on the code. Okay, thanks for watching and have a good day. Bye.